And good morning, all my wonderful friends. Thank you for coming along. Yes, incoming, as Michael says. G'day. Oh, there are a whole bunch of people here. I've been being the daddy taxi service. I just took my daughter to the station, and I'm back just in time. So I acknowledge the traditional owners of this land. I pay my respects to their elders, past and present, and to Aboriginal elders and peoples from other communities who may be taking part in this live stream today. Now, this live stream, the temptation is strong to just play a bit of Portal or The Last of Us or something like that to distract myself. You know, have one of those mornings where I just sit in front of the screen and do some gaming or something and have my mind wander around. I'm almost in the cam. Is it zoomed in too far? Yeah, I was actually doing some filming of real proper edited videos yesterday, and the result was that I had moved tripods and I had to take the camera and move it somewhere else, and it was all rearranged and I had to put it back. And I'm trying to get it in a position where I can see straight on at the computer, and also I can see a bit when I'm at the workbench. What's Steve looking at? I don't know. Steve is doing his own thing. Let's turn Steve around. Steve can join the party. The tape is starting to come off a little bit on Steve's. Hang on. I've got to get myself in the camera. Yeah, I've got to sit sort of sideways in order to get myself in line with the camera. The computer is off to my right. Right. Okay. Good morning, everybody. Yeah, so as I was saying, the temptation is to just put my brain into a different place, and I've been spending way too much time over the last few days, as I'm sure most people have, sitting there doom scrolling through Twitter and looking at stuff on Facebook and wherever, getting whatever information we can about what's going on in Ukraine. So this morning I thought that what I would do is just spend a bit of time putting together a PCB, and we'll see if it works. It's one that I designed a little while ago. Well, when I say a little while ago, a month, 6 weeks. And it went off for manufacturing with a batch of other PCBs. It came in. The other PCBs had priority because they were for customers, so I worked on those. And this one has been sitting there just taunting me, saying, assemble me, assemble me. So today is... Yes, today is going to be, I'm going to be deliberately relaxed. I'm not going to be rushing through anything, and I'm just going to have some fun putting a board together. Now, what have I missed? I don't know. Oh, one thing. I've kind of got to, I'm going to share this because it's just kind of annoying. It's a frustrating thing, and it's a follow-up to something I mentioned last week, which was that I had just bought a Stream Deck, and it turns out that it never came, and I may have lost my money on it. A bit of possibly a Gumtree scam, but I don't know. So where are we? This one and this one. If I can get myself in the right position. So yeah, this is the add-on Gumtree, which is still up, as you can see, and it was 180 bucks. Offers welcome. So anyway, what we ended up doing was I made a lower offer and then added postage onto it and stuff. So we ended up coming to an agreement that I would buy Jeremy's Stream Deck for 170 bucks, including express post, and it all went okay. I got his mobile number, which I haven't actually checked if it's the same as this one. I'll have to check. So yeah, he seemed quite genuine in chat, and we were talking for a few days about arrangements and things, and then he confirmed that payment went through, and then the day after he said he was going to post it. Haven't had a word since then. So I think it's been 6 days since the last message from him, and I've sent messages to him saying, are you a scammer? Well, not quite. I sent a message to him this morning saying that at this point I've got to assume one of three things. Either you've been in a car crash, you caught COVID, or you're a scammer. So maybe it'll work out. Maybe it will unexpectedly arrive. But, okay. So let's get out of that. Oh, yeah, you're right, Austin. I shouldn't have done that. I did that on stream when I shouldn't have. Oops. Oh well. I can go back and edit the live stream later and remove his phone number. Nothing I can do about it now while the stream is going on. So this is the board for today. This is it in Vision 360, so we can see what a representation of it looks like. And the purpose of this. Okay, I've talked about this before, but let's kind of do this in a concise way. The background to this, if I go back to here and here, is that I need a controller for this conveyor belt system. So it's all kind of hanging around loose at the moment. So this is a conveyor belt to, got to get into the middle, to carry PCBs between pick and place machines, or between a pick and place machine and an oven, or from like an input side going into it from a board stacker, or as an inspection point between machines. So what it could do, for example, is have boards come in from one machine, they stop in the middle, and then you put parts on it, things that have to be manually placed that can't be done by the machine, and then it can go on into the reflow oven. So it could be like an inspection station or whatever. And it has a fixed front rail, and the back rail can move so that it can suit different sizes of PCB. And the idea is that rather than being like a big flat conveyor belt, it only touches the edges of the PCB. And that is so that if you have a double-sided board, or if you've got a board with through-hole parts that you're fitting and they've got legs that go through, it's not going to interfere, it's not going to sit on anything coming through the board. So yeah, you can do things like pick and place machine might put a connector in place that's got some locating pegs and they stick through the PCB a little bit or something like that. So it only touches the front and back edges of the board or the panel. And this is the conveyor belt that moves the boards along. So what I need is a couple of things. I need a controller that will run the motors to move the conveyor belt. I also need to move the stepper so that the back rail can adjust its width to suit the size of the PCB that you're passing through it. And I need sensors so that it knows when a board has entered or left the conveyor, so that it can do things like stop automatically once it's unloaded a board, and also so that it can do things like move a board to the center position and stop it until you press a button saying you've done your operation on it and it needs to be taken off to the next point. So it needs input and output sensors and all that sort of stuff. So what I've been doing is experimenting with one of these little ESP32 touchscreen modules, and I've got a whole bunch of jumper wires in it, and there's a little stepper motor controller module there, and what is that, a voltage regulator, and so I've got it all cobbled together, but at the moment it's using DC motors for the movement this way, and it's using a stepper motor for movement this way. I'm going to change it to using steppers for everything, so I'm going to use little NEMA 8 steppers in the ends here to move the conveyor belt so that I can move to a known position by counting steps and all of those sorts of things. So the exercise for today is taking this cobbled together thing and putting it onto a nice PCB. Now I've just been watching my, I just saw that one of the VU meter on the ATEM is way into the red. Is my audio level way too high? I think I'm just going to turn it down a little bit. So if I go quieter, that is probably going to be less offensive on your ears. So where am I? Okay, I've got an assembly guide here, and because I've run out of what color is it? Yellow. I think I've run out of yellow in my printer. It refuses to print in color at all, so I've had to print it in black and white. I've got a board here, and oh, that's right, we can go fancy, because I've got all of these set back up again. I should be able to go camera 3, and here we've got the PCB. So this is the PCB that I was just showing on the screen, the one that I had open in Eagle, and it's it doesn't really have all that many parts to put on it. I do have a stencil for it, and I printed one of Sion's little vacuum adapter things. So here is the stencil to suit it. I got a frameless stencil this time because I was going to use it with the vacuum adapter. So this is a little vacuum adapter plate for the board to sit in, and that sucks the stencil down onto it. So I'm not going to use that today because I'm only going to be assembling one of these, and my setup is in a big mess right now actually, because we've actually, I'm going to show you something else. I'm going to show you something else that's going on in here at the moment. Let me see I've got to think about what screen I'm working from. All right, camera. I'm just going to show you a photo of what my bathroom looks like right now today. Although I took this photo yesterday, but still, it'll give you the idea. I've just got to find it. Where is it? Here. Okay, I'll bring this up where you can see it. So this is the inside of my bathroom right now. And this is the area where the shower alcove used to be. So that's the drain from the shower, taps up there. So we have a bit of a, you could say we have a bit of a hygiene problem at home. So we have a lack of bathroom right now, and it's probably going to be about a month, give or take, that we will have no bathroom. And now, as you would have seen before, there is the little bathroom that's in the back of the lab here, sort of over my shoulder, back past Steve. But it's never really been used as a proper bathroom, which means we never even installed a shower screen in it. It was fitted out, all tiled, all plumbed, but no shower screen installed, and there's still no shower screen in there. And then I put a rack in and filled the entire shower alcove floor to ceiling with a rack which had my Reflow oven on it and a whole lot of other stuff stored in there. There was my second 3D printer was in there and a couple of other things. So I've had to empty that bathroom so that we could use it, which means that my Reflow oven is currently sitting in the garage, and we had to move stuff out of the garage into the house so that there'd be room to move stuff out of there. Anyway, my space problem went from being bad to being really, really bad. And in fact, my part storage, most of my part storage is inside the house now. So it's like, it's a few doors away from me. I've got to take quite a trip just to go and pick up a package of whatever. Yeah. Oh. Crispian says, I saw a shower screen on Gumtree yesterday. Yeah. I think I'll pay for that one with a with an online bank transfer that is has no protection and no recourse. That sounds like a great plan. Yeah. So we are getting a shower screen installed. We ordered it actually 2 weeks ago or so, but they had to cut a custom piece of glass, and the rest of it, like all of the frame, is done. Sometime in the next few days we should get a shower screen installed in there, and then it'll be fine again. We can use it, but it still means that all of that extra room that I was using for storage and for reflow and things, and I'd even set it up. So what I had done is built a fume cover, a fume hood that went over the reflow oven, and I took the exhaust fan out because it's a bathroom. It was wired up with a, you know, the standard round exhaust fan, and I took that out and then got some of that big silver exhaust duct, and I ran that from the fume hood up through the hole where the exhaust fan used to be, through the ceiling to a big extraction, like a fume extraction system that I put up inside the ceiling, and that is plumbed through, well, when I say plumbed, I mean like air conduit to an external vent, and then the air gets dumped outside. So I'd gone to the extent of really setting it up pretty well as an enclosed space that I could use for doing things like reflow, and now I can't do that. Sounds like I've missed most of the comments, but I just happened to notice Jay Hill said, not sure this is the place to ask. Yeah, it is the place to ask. Is international shipping still suspended? It's not, but it's not back to what it was pre-COVID. So what happens with international shipping is, if I try to ship a package using standard class, economy class international shipping, I can't get a customs clearance from the destination country, is typically what happens. So if someone orders something from me and they specify economy shipping, I either can't ship it, or I have to upgrade the shipping to standard and then pay the difference myself, which is usually what I do. So, and also international letter class packages are not being carried at all anymore. They're just not being accepted, which really sucks for electronics, because a lot of the time when we're selling stuff, I was just looking around for an example of something, like the hobbyist sort of products are typically a circuit board with some components on it and in an anti-static bag, you know, with a sticker on it or a card clipped on or something. The whole thing is quite thin, which means that it is ideal to stick in a padded bag, and as long as the whole thing, including the bag, is less than 15 millimeters, it used to only cost, how much was it? $2.20, I think. Yeah, $2.20 to ship a padded bag internationally anywhere in the world, which was fantastic because, it meant that you could sell low value items and ship them internationally if they were thin. And I used to, I've got boxes and boxes in the garage of padded bags because I used to send so many of my orders out in padded bags using letter class international packages, but you just can't do that anymore. So the summary is, international shipping is working, but it's really only working for standard or above packages. Letter class and economy, can't really do it. Yeah, Sion says there won't ever be electronics in letters anymore. Yeah. It would be nice if that came back again, but I don't think it will. Everything has changed. The economics of things have changed. The volumes of things have changed. So, yes. Where was I? That's right, I was assembling a board. 20 minutes in, and I'm still just randomly talking. All right, where was I going to go with this? Okay, now something I should mention just in case I don't get to it or I forget about it later. On Twitter, Austin talked about putting solderable standoffs on these boards. So this one here, so this is the touchscreen thing that I was talking about. It looks really dark. I wonder what the brightness setting is like on that camera. I may need to change the ISO setting. So this is a touch screen I think that way technically is up. It's a capacitive touchscreen, and on the back it's got an ESP32 and headers. So you can see there are two headers here. It's got a couple of big voltage regulators here. It seems to be a pretty decently designed board. There's a USB-C connection for which you can either power it through or program it through. There's a Scilabs chip on it for USB to serial conversion. I think it's a CP2102N, so decent chip on there. It seems to be a really well designed, nicely engineered board. Now the reason that there are two connectors on here is that these are actually identical. They have duplicated all the connections. The connections that are on this are the same as the connections that are on this. And so when you are designing something to fit onto this, you can choose which one you want to use depending on the orientation of your design. Like you might be making a vertical format screen or horizontal format screen, or you might have connectors that you want to use near an edge, and so you need to keep one side of it clear for through holes and things. So what I did with this board was design it to use this header along the long edge here. And the idea is that this is actually the first time I put it on top of here to check. Yeah, I designed this based on dimensions that I was figuring out from this, and I really hope that I got it right. So what I did was I worked off the bottom connector, and then this is going to sit on the back here with standoffs in between. So you can see there are holes in the corner here, and they are plated holes. So this is going to sit somewhere around about there, directly behind it, and it will have the connectors on it for things like the stepper motor drivers and inputs from sensors and all of that sort of thing. And then that'll mount in an enclosure on the front of the conveyor belt assembly. And you can see here there are a couple of headers for little step stick modules. And I did not incorporate the drivers directly on the board for two reasons. One is that I'm lazy and I already have some of these modules, so I can just plug them in. And it means the modules can be interchanged if you want to use this for different purposes. But the other thing is that there is a different use case for this which will require a custom module, and I've got some of those PCBs too. We may get to that. We'll see how we go. Anyway, that's right, I was talking about stencils. Oh, and after that I was talking about Austin's comment about solderable standoffs. So Austin has also just recently designed a PCB that goes onto this same WT32 SC01 board. And I think Austin's board has PoE on it, so he's added Ethernet. And that was my original plan for this, was I wanted to have Ethernet so that I could plug the conveyor belt controller into the LAN and then just send messages to it via MQTT or whatever. And I ended up not doing that. Sorry, I'm just checking the visual alignment here. It seems to be right. I think the dimensions actually worked. I'm kind of stunned. It's amazing. The holes all line up. Oh, hopefully this is going to work. It might. We'll start a tally, see how many mistakes I made. So far I haven't started assembling it, so the error count is 0, but that is likely to go up. It's very likely to go up. It's very unusual for a V1.0 board that I make to be all correct. So, solderable standoffs. Yes, I don't have any solderable standoffs, but what I do have are these heat set nuts or heat set inserts. These are intended to go into plastic. So the idea is that what you do is heat them up, and I've got a soldering iron tip here that I use just for this purpose. It's clean other than having been used for this, and it's about the right size to go into it. So what you do is use some kind of a heat tool to heat this up. And there you have a hole in the plastic part that is just slightly smaller than the diameter of this. And when it's hot, it melts its way in, and then you pull the heater tip out, and you're left with a brass threaded insert in your plastic part. And for 3D printed projects, this is amazing because you can 3D print a thread, and you can also just print a hole slightly undersized and then screw into it, and the screw cuts the thread. And that's what I pretty commonly do, particularly for things that you're just going to screw together and then leave them screwed together. The advantage of this is that you can screw and unscrew into this threaded insert and it doesn't degrade. If you're going into a 3D printed thread, then it gets cut out over time and yeah, it doesn't necessarily last very well. But with these brass inserts, you can put a little M3 bolt into this and then take it out later and then put it back and take it out. It's going to be fine. So I've got them in a few different styles here. And these, what are these ones? M2, yeah, these are M2 heat set nuts. These ones are M3. I've got two styles of M3. And I've actually already put these into the other board. So I've got two of these modules. When I bought them, I didn't know what they'd be like. I just wanted to check them out. I ordered two to have some to experiment with. This one has never been powered up. I've never done anything with it. It's just been in its box as it arrived, and I'm going to be trying it. But on my other one, what I did was solder heat set nuts into them. Now, if I switch over to, where can I go? Microscope? Yes, it works. Amazing. I've just got to get it in the right position. There we go. So that is one of the M3 heat set nuts. It's kind of a bit zoomed in for something this big. And in the bag, if I bring this in, you can see that is a different style of heat set nut. You can see that this one's symmetrical. It's got a little ribbed section or a knurled section on both ends, and it is symmetrical with the thread all the way through. Oh, hang on, maybe it's not symmetrical. I just noticed that the thread seems to be, oh, doesn't matter. Anyway, the thread goes right through, and on the outside it is symmetrical. That's the point. Whereas this other type, this other style that I've got, this is also an M3 heat set nut. You can see that it's not symmetrical. It's got a narrower section at this end where it is meant to be inserted into the material. So you start by inserting this end, and then it goes in until the surface of the material matches this edge here. So this is the, oops, it's very hard to see when it's, the microscope is zoomed in that much. So this is the side that the bolt goes in from. Goes in here, and the other side is inserted into the material. Now this particular thing, this style of M3 heat set nut, I discovered works perfectly with these boards. I'll just see if I can get the position there right. So that is the corner plated hole on this touchscreen PCB. And if I grab myself some tweezers and get the heat set nut and sit it in that hole, trying to watch what I'm doing through the camera, which does not work very well. It works perfectly because the little narrow bit at the end drops into the hole, and then the wider part of the nut stops it going any further. So it ends up sitting perfectly square against the PCB and perfectly centered. It's like these were made for it. It's brilliant. So on the other one, what I did, and then you can just hit it with a soldering iron and some solder on the outside and solder it in place, and then you got yourself a brass threaded insert in the PCB. Now the ones that Austin used are actually standoffs, so they are longer, and these are very short. They only stick out of the PCB by, if I bring this one back over here, if I can, where's the microscope? Come on, there it is. Yeah, so this bottom narrow part goes into the PCB, and then it sits on, I need better tweezers for this purpose. It sits on this face, and then this is the distance that distance there, that knurled section, that is the part that protrudes out of the PCB. So it doesn't really provide you a very long standoff. It's only a few millimeters. In fact, let's find out. I'm going to stick the calipers on it. It is 3.15 millimeters. So the distance from there to there, 3.15 millimeters. Yeah, this microscope is way too zoomed in for that sort of thing. But what I can then do is use a spacer or something, and I can use different size spacers to adjust where the PCB is going to fit relative to the back of the touchscreen. So I'm going to get back to that. First thing to do is get the PCB assembled, and then come back to the touchscreen later. Now, I was talking about stencils earlier. Now, most of this is actually, it looks like a fairly complicated PCB just because of all of the printing and things all over it. But it's actually not. In terms of the surface mount parts that go on here, there is not really a whole lot. There are big spaces that are taken up by things like these IDC headers. These are pluggable screw terminals. These are the headers for the modules. We've got a couple of big electrolytic capacitors that will go in these spaces here. Relays up here, power supply module, big switch. So when it all comes down to it, there's a CAN bus transceiver here. There's an MCP23017 here in the small outline package, whatever it's called, SSOP28 or something, I can't remember which one is which. There are a couple of opto isolators here because we've got opto isolated inputs. These relays are for the like dry contact outputs, and these are pluggable screw terminals, one on each side for CAN bus and power. So with all of that in mind, my plan is just to stick some solder paste on with a syringe and just do some reflow with the hot air, which is not really how I like doing these things. So part of the problem with hot air is that it is fairly selective in its heating, and the temperature profile is not controlled. It's just controlled by you sticking you're controlling where you point the thing and how long you hold it there. And you don't have any feedback, like no actual measured feedback on how hot things are getting. So you kind of just got to use your own judgment. Now, can you see this? Yeah, kind of. Okay. Yeah, you kind of just got to use your own judgment as to how you are reflowing things. So it's not ideal, but I'm only doing this one board, and my reflow oven, as I said, is currently sitting in the garage. It's in a location, I haven't leveled it, it's just sitting on a bench. The bench, I am pretty sure, is not level. So yeah, I would need to do a bit of work to level it up before using it. And I always end up missing pads when I'm doing this. What am I saying? Reflow, that's right. So I could use it, but I would need to do a little bit of work to get it set up. And then one thing I've discovered, sorry, I was thinking of a tangent to go off on, which is so out of character, about leveling reflow ovens. Yeah, okay. So you might wonder why leveling is important. The reason is that when the solder reflows, obviously it becomes liquid, and it just follows gravity. Follows gravity and heat, the two things that influence it. Solder tends to run towards heat, and obviously it runs towards, like water, the lowest point it can find. Have I done everything? Surely I did not just paste every location on the board. I'm just sort of angling the board and making it reflect. I'm using the lighting to reflect off it, off the silver parts, to see if there are any little silver spots that do not yet have solder paste on them. And it looks like I've got it on everywhere. which is cool. So, time to switch back to, what am I doing? Switching back to the overhead camera, which takes a while to switch because the Panasonic's output has to adjust itself when it detects the new device that it's talking to. So, what do we need? Now before this morning I went into the house and, why won't that come out? And I think that I have collected all the parts that I need. I may actually have to run inside the house to grab something else if I've forgotten anything. Let's begin by putting this chip in place. I should probably switch back to the microscope in a second. Well, that footprint seems okay. So this is the MCP 23017 sitting in place. Now, what else do I need? I've got my handy assembly guide here. I'm going to grab my resistor box and start putting stuff on. I tried to minimize the parts values that I need, so it's mostly 10K, 1K and 4K7 resistors, with a couple of exceptions. What have we got? 10K, where's 10K? I'm going to tap it just for luck. Make all the parts fall off the bottom of the lid. Where am I looking? There. Oh look, there are hairs in my... little hairs stuck in it. Hopefully I won't have... Oh, look at that. There's a hair. That one's not mine. Yeah, once I move into the new lab space and get the clean room set up, there's going to be no dog hair and no human hair and no cat hair. It'll be so much better. 10K. These are the bias resistors on the MOSFETs that drive the relays. 10K. And what's that one there? That is a 560. Because it is driving... What is it driving? Oh, one of the optocouplers. Yeah, so... optocouplers. Is that where a 10K goes? Yes, it is. So... What else am I looking for? Are there any more 10Ks? I don't think so. I think I've populated all the 10Ks. Time to go to 1K. Yeah, so what I've done is allowed for both upstream and downstream interfaces, because if this is if this conveyor belt is connected between two pick and place machines, or you know, a board loader and a pick and place machine or whatever, it needs to know upstream when it needs to communicate with upstream so that it can say to upstream, yes, I'm ready to receive a board, or no, I'm not ready to receive a board. And it needs to communicate with downstream to say, are you ready to receive a board, or yeah, do I have a board for you? So yeah, anyway, so there are two sets of ready in and ready outs, one on each side. And also I like things to be symmetrical. It's kind of a, I don't know, what's the term? I was going to say OCD, but I don't know, maybe it is OCD, but I just like it when boards have symmetry, so things are the same on both sides. Now these are, that's a 4K7, which is going to be an I2C pull-up, and here's another one. I could have just made these 10Ks as well, so that it's one less part value to be loaded in the pick and place job. Now this next one is a value that has to be different to everything else. Well, it's got to, no, it doesn't have to be different to everything else. That's the wrong way to put it. This is the 560 ohm resistor that goes through the optocouplers. So for these ready in and ready out connections, what I've got is optocouplers on the inputs so that it can read the adjacent machine's output, and we don't know what that output is going to be. So by using an optocoupler, and then in software logic we can do things like detect an active low or an active high or whatever it needs to be. Now what goes there? There is a resistor there. That is the E-stop. E-stop. Interesting. This assembly diagram that I'm looking at is obviously older. If that's E-stop, it will be VDD and sleep. That'll be just like a 10K. It'll be a pull-up. So I'm going to just stick a 10K on there. I wonder why the version... Oh, I know why. It's because I migrated this project from Eagle to Fusion 360 partway through. So the final part of this board design was actually all done in Fusion 360. I started it in Eagle and then converted it. And so when I printed the assembly guide out of Eagle, it doesn't have the most recent changes on it, which included the E-stop input. Now, on so E-stop is emergency stop, for anyone that hasn't come across that before. The idea is that if things go wrong and you need manual intervention, you can hit a big red button and it just makes everything stop immediately. If stuff is on fire or it's bashing into something or it's about to jam your hand or whatever. So, oh, that is the can... I'm distracting myself by... No. Yes, I'm distracting myself by talking about that when I'm actually trying to do assembly. I haven't looked at the chat since, I don't know, like 20 past 10. What's the time now? 10:43. So I'm 20 plus minutes behind on the chat. I have no idea what you're all talking about. I am just going to continue mumbling away to myself and work through this, and then later, if there is anything critical that is in the chat that I missed, someone can shout at me or send me an SMS or something. Okay, so next I'm going to put on the 120 ohm termination resistor. Now this is, I am kind of embarrassed about this. I've been doing this incorrectly for a few years now. Now, CAN bus needs a termination resistor on both ends of the bus. Now, if you only have two devices connected together, you have one termination resistor in each device. If you have three devices connected together, you have a termination resistor on the end devices, but not in the middle device. And the simplistic way to look at it is you just stick a 120 ohm resistor across the CAN high and CAN low. Now, I'm getting to the point here. You see that? That is an 0603 resistor, which is rated to, what are they rated to? It's like 1/16 of a watt or 1/10 of a watt or something. And that is part of my point. So this is the 120 ohm CAN termination resistor. And I read an article a little while ago which was talking about CAN bus and possible failure modes and how things can go wrong in a really, really bad environment. And so what this thing did was look at failures that have been seen in real life, and also looking at possible potential failures. So if you've got And there is one thing that so anyway, back to the point. I have previously been putting 0603 120 ohm resistors as the CAN termination resistor in my projects. I've been doing that for years. I've put it on many boards. And in this article, it was talking about the possible current through the termination resistor in a fault condition. So the idea is to be thinking about not just what will work, but what will not be destroyed in the worst case scenario. And so there was a little calculation that, so this resistor, this CAN termination resistor, is directly between the CAN high and the CAN low lines. So I don't know, I can't remember which is which, but these two lines here, one is CAN high, one is CAN low. And then there is a protection chip on here as well, which I might get to in a minute. But anyway, CAN bus comes in, oh there we go, CAN high, CAN low. Comes in on this pair and comes into the CAN transceiver. And then this resistor here is wired directly across, if that jumper's in place, directly across CAN high and CAN low. And it terminates the line. Now, if you have, see we've got positive here, so we've got positive and negative supply input, and we've got CAN high and CAN low. What this analysis talked about was a scenario. Say you are running on a 24 volt truck, and the truck, like a worst case scenario is the truck's alternator is running over voltage. So it's actually, you know, you're running at like normally 27-ish volts, and then you might be as high as 28, 29 volts. And then you have a short circuit that occurs between that, like say there's a wiring fault in the truck, and you get a short between the positive, which might be say 29 volts, and one of the CAN lines, like CAN low or CAN high. Say you put 29 volts shorted into CAN high, and it is, and CAN does need a reference ground. It is not a pure differential pair that's floating relative to anything else. It needs a reference ground. So if you short circuit, say 29 volts into one of your pairs of a CAN bus, you might have 29 volts running through a 120 ohm resistor to ground. And when you do the calculation on it, what it means is that an 0603 resistor just isn't going to cut it. That's going to become a fuse. And the system will probably still keep working. So say you blow your CAN termination resistor and it goes open circuit because the thing has just smoked, it's off the board, and then the truck or whatever it is fixed and everything is working again. Your board will probably keep working, but it won't have a CAN termination resistor anymore because it'll be a black spot on the PCB. So what you need to do is, in the sizing of the CAN termination resistor, you have to allow for a load dump voltage going straight through it to ground. And so anyway, I recently bought myself a how many did I buy? Like 500 or something, I can't remember, of these high wattage 120 ohm resistors. So that's what I use on all of my CAN projects now. Now, there is actually a better way to do this CAN termination in really noisy environments. So what you can do is use, so this is a single 120 ohm resistor. This is really getting off topic, but it's kind of interesting to talk about. So let's switch, where am I? I'm going to switch to overhead and light switch limit. Oh, this is my my lab notebook from the PCB conveyor project, and I was just going to, yeah, you can see different strategies for things and how my wiring is going to be, and motor mounts and then pin outs. So this is all my notes that I've taken over the course of working on this. Sometime I'm going to talk about my lab notebook strategy as well. I have very specific ideas about that and how they should be used. So let's see how we go here. All right, so can termination. Say you have can high and can low. Can you see this? Yes, you can. So say you've got high and low coming in from somewhere. The usual way to do can termination is you just stick a 120 ohm resistor straight across these, and that goes into your transceiver. So that'll be your can transceiver, and that's it. Like, if you've done that, you have complied with the requirements. And in fact, this is what is on this board here, except that the traces come off the other side. But anyway, that's not really relevant. But for real noise immunity in a really bad environment, there is another strategy you can use. And I haven't bothered with this because this, I think, is something that's generally done if you have a really extreme situation. And what you do is take, so you've got your can high and your can low through here. I'm going to bring it down to give myself some more room and bring it up there. So imagine that it's the equivalent circuit. So what you do is, instead of having a single 120 ohm resistor as your can termination, you bring it down to a 120 ohm, into a 60 ohm. So that's a 60R and that's a 60R. You have two 60 ohm resistors in series. And then from the center tap, you bring it down and you take a capacitor to ground. And what this allows is better noise immunity on the CAN bus. So you still get the 120 ohm, what do I call it? Loading DC bias or something. And this is applying a bias to the center point of those two resistors. Anyway, I don't know what the value of this capacitor is. It's a little while since I read the article that was doing the analysis of the optimal way to do it. But anyway, that's the general concept. Where was I? Back to putting stuff on the board. Now, CAN termination resistor. That is done. What did I just do with it? I just put those on the board. Somewhere right in front of me on this desk is, or maybe I put it back behind me. No, I didn't. Somewhere on this desk, there it is. There it is. I lost it on an almost empty desk. That is, oh, it's 1,000. Yeah, so I've got 1,000 of those 120 ohm 3/4 watt resistors. So they are 2010 footprint, much bigger than a normal 0603. Now, what else am I going to put on? Opto isolators and the Schottky I will leave off for now. CAN protection TVS. So this is the protection chip. So this is part of my my part storage strategy as well. You can see I've got my own label on here which has barcodes that will take me to the order pages, like the order codes for both DigiKey and LCSC. And on the bottom it says what category of parts it's in, which matches my Eagle libraries, which are also organized to match these categories. And then I have storage boxes that these get grouped into. So that one's diodes, this one's LEDs. For example, the opto isolator goes in the LEDs box. That's a bit of a strange one, but it's just the way it is. And typically I stick on the actual label from one of the times I ordered it, so that I can see all the DigiKey information and stuff. And a lot of them, like this one, you can see that I've ordered these from, in the past I've ordered these opto isolators from both DigiKey and LCSC, so I've got both of their labels on there. So, protection, yeah, so TVS, TVs, it stands for transient voltage suppressor. It's a little SOT23, so it's a 3-pin package, and it is a pair of Zeners, I believe. And what this does is acts as a voltage clamp on the CAN bus. So it provides some extra protection of, yeah, against bad stuff happening that could destroy the CAN transceiver. And where are we going to put it today? We're going to put it there, but it's upside down. Turn it over, and that sits right there. So that's the transient voltage suppressor. And what you can see here is the CAN high and CAN low coming in, and then the 2 pins of the transient voltage suppressor are connected to those 2 lines, and the 3rd pin, which is this one right in the middle here, goes to ground. So what's inside this SOT23 package is a pair of Zener diodes which act as shunts, and if the voltage on here, on this data line relative to ground, goes above a certain point, it conducts through here. So it cuts the top off high voltage transients. That's the general idea. And you can see that I've put a via there and another one there to stitch the ground plane through to the other side of the board as well. So it's got a nice big solid conductive area here as well, which is good. But I also wanted to make sure that there was stitching quite close to that. So I just threw a couple of vias in there for the fun of it, sprinkling them around like confetti. What else am I going to put on? Let's put on some transistors. And these are going to, oh yeah, so this is how I store reels when they're not in use. I stick them inside bags to keep them dry. What have we got here? 2N7002 is a spare reel. There's another reel on my pick and place machine, but this one, this one I have not, yeah, it hasn't been loaded on a machine yet, so I'll just use it for, good, dunk, there we go. Take the first couple off the reel, and these are for controlling the read relays that act as the outputs on the interfaces to the adjacent machines. Where am I? Yes, here. Okay, so that is a 2N7002, just the classic cheapy N MOSFET that everybody seems to use. It's one of those things where, you know, if you get onto electronics forums, people will go on about how crap the characteristics are of the 2N7002. And they say, don't use that. It's a dodgy transistor. It's been around for decades. But it just keeps being used. And I keep using it. Okay, so I can put on some of these little MMDL 914s, which are diodes. Same deal, I've got a reel here, which you can't see because I haven't switched cameras. I've got a little reel of these diodes. I'm going to stick some of these on. What are these diodes doing? I don't even remember. I'd have to look up the circuit to remind myself of what is going on with them. What are they related to? Oh, I think they are related to the board sensors. So what I'm doing is using time of flight sensors mounted at the ends of the conveyor belt, and the time of flight sensors are mounted sort of, they're not physically on that one that I was just waving around, but I've been doing some testing. Oh, come on. Oh, come on. Why is it that every time you turn over a part, it ends up facing the wrong way? So the, where are we? There's the other one. So the board sensors are the little laser time of flight modules, which are remarkably cheap. They're one of those things that when you hear about them, you think, that is technically amazing. How does it even do that? Like, it sends off a little laser light projected off, and then it measures how long it takes for that laser to be reflected back from any surface in front of it. And from measuring that time, how long it takes light to travel a few millimeters, which is not very long, it can figure out how far away the thing is to quite a good degree of accuracy and resolution. Quite astonishing. And you can buy the things for a few bucks. It amazes me. People are amazing. People who design these things are just incredible. And we get the benefit of it, which is so cool. So yes, laser time of flight sensors to detect when a board has arrived at the entrance to the conveyor or when it has finished departing from the conveyor. At least that's the theory. I've connected up the time of flight sensors, and I've verified, just with an Arduino connected to them, that I can read from them properly, and they're really easy to use, and that they do work at the short distances that I'm talking about, because they're actually designed to measure ranges out to a couple of meters, out to a few meters. And they're not really designed to measure things that are really close in front of the sensor. Hang on, why did I just... I'm doing stuff without even thinking about it. I guess I'm talking. This is the CAN bus transceiver. And because everything on this board, almost everything happens in pairs, and I was talking about other stuff, I just took 2 of those chips off the reel when I only needed 1. Because of course there's only 1 CAN bus transceiver in this project. There aren't 2 CAN buses. We only need 1 transceiver with 2 connections. So, where was I? I don't know. I don't know. So how many diodes do I need? I've got to stop and pay attention to what I'm doing. Yes, I only need 1 diode. So this is a Schottky diode on the input side, bit of reverse polarity protection. So just in case. And the idea with this is that this connector on the end, which has got the CAN bus connections and has the power supply connections, you can see the positive connection from here, the big fat trace comes down here to this diode. So I'm going to stick a Schottky diode on there. It's an SS56. The value is not particularly important. I could have just put a 1N4004 or something on there, which would be my usual go-to just silicon diode. But Schottkys have a lower forward voltage drop and, oh, hi Steve, and higher current rating. So this one, these SS56s have a 5 amp current rating, and 1N4004s only have a 1 amp current rating. And I want to be able to, so this power supply that comes in from here, coming in through this diode, and then it comes to this switch, which is the main power switch. That power supply is going to be running the stepper motors. And I wanted to, having a 1 amp diode there in line with the power supply, I thought would be kind of cutting it close. Better to have a 5 amp diode just so that, we've got headroom. Everything is good. Am I running out of parts to put on this board? There have got to be more. Opto isolators, yes, I can put on the optos. And what else? We may be just about at the point where I can start waving some hot air at it. Let's see if I can melt it into submission. Okay. Opto couplers. What are these ones? LTV816S is the value of this particular opto coupler. 816D it says on the package. According to the part number, it's an LTV816S, dot to dot. And then the other one at this end, got to align that, dot to dot. Ba-boom. What else can I put on this board? Do I have any solder paste left that does not have a part sticking in it? I think I don't. I think it's time to, yeah, spin up the hot air. I'm going to get myself a little bit of cardboard. And yes, that is not the ideal thing, but let's do this. In fact, I'm going to do this under the microscope. I don't think I would normally with this sort of size board, but I'm going to do it under the microscope so that you can see what's going on, because it's cool, or hot, but cool. And I'm going to use my old-fashioned hand to turn on the soldering iron, because I'm not going to use she who shall not be named, which I could do. Where am I? Oh, there, okay. So I'm going to start, the way I'm going to do this is I'm going to start on the right hand side of the board, which is not entirely random. What I want to do is kind of minimize thermal shock. So I'm going to start on the right hand side of the board. I've got the hot air in my right hand, which means that the hot air overflow, like the spill, is heading off towards the left. And so what that does is, as I progressively move the board from left to right, and I move the hot air along it, the parts to the left that I haven't quite got to yet will have already begun to warm up, so they'll undergo less thermal shock. At least that's the theory. Oh, come on, you stupid little 560 ohm. Pull into, come on, surface tension, do your thing. There we go. Yeah, so I'm keeping the hot air actually quite some distance back away from it. The objective here is to do like a gentle warming process. You can see the ground pad there is not flowing. It's taking a while to flow because it's being thermally wicked away onto the big polygon on that optocoupler. How are we looking here, folks? All right, this is a CAN termination resistor. Yep. Got a bit of nice reflow on that. And that 10K on the e-stop. That's right, e-stop. I was talking about e-stop earlier. Let's talk about e-stop just for a moment, because there are a couple of different ways to do it, and I've wanted to allow for both. Now, you can have like a soft e-stop or a hard e-stop. And now, I'm just kind of making this terminology up because I don't know anything about this stuff. I'm just figuring this out as I go. But the way I've seen it done, you can have an e-stop which is in line with the main power into the thing. So if you have one of those big red panic buttons that you hit and it turns off power to everything, then yeah, that's like a, oops, ow, I'm burning my fingers here. Then that is one way to do it. But you can also have a soft e-stop where you send a logical signal to the device and it does some kind of a more controlled shutdown. We'll get back to that chip in a moment. And so in order to allow for like a hard e-stop where you just cut the power, there's nothing I need to do on this board because that can all be done externally. But what I wanted to do was also allow a soft e-stop. Have we got any solder bridges or anything happening there? Oh, look, there's a hair that I can see. Just check the focus. There's a hair across the pads there, I think. And is there anywhere on the board that I haven't been yet? You can see there are a couple of solder board balls there. Anywhere that has not been reflowed. And I'm kind of being nasty by moving this thing around like this. Ideally the board should be staying stationary. It shouldn't be moving around because, as you've seen, when the solder is molten, oh yeah, this needs a bit more reflowing, I think. When the solder is molten, the parts move around. And this comes back to what I was starting to say earlier about leveling the reflow oven. If the oven is not level, you can end up with solder migrating from one side of a part to another, and you get more frequent tombstoning and those sorts of effects. So it's kind of important for reflow ovens to be nice and level because liquids like to go downhill. Alright, time for a quick visual over the thing and see if there's nothing bad going on. Nothing excessively bad that I can see. There are a few little solder balls that I'll need to pop off. Well, probably don't need to. They're not likely to cause a problem, but I don't like leaving them there. But the board is still quite hot. It'll be taking a little bit to cool down. Yeah, stuff it. I can jump the gun. Now, where were those solder balls? Up here on this transistor. Yeah, so e-stop. So what I've done is over here, where was it? Here, no, there, where it says e-stop. This is, I didn't really know how I wanted to handle this. So I left it for a future decision. I deferred the decision. What I did was I just took a connection from here. So you can see this is 3.3 volts, I believe. The VDD connection must be 3.3. So this is a pull-up to 3.3 volts, and I've got a 10k resistor on there. And then these two pins, you can see one of them goes to ground. This is the ground plane on the top. So if you short that, it pulls to ground. Now, on the other side of the board, there is a trace that goes from here. You can't actually see it. What it looks like here is that we've got a 10k resistor with a jumper that just pulls it straight to ground from 3.3 volts, which would do absolutely nothing except burn a bit of power. But on the other side of the board, there is a trace that goes from here, and it runs to one of the GPIOs on the header to the ESP32, so that the ESP32 can detect whether this has been shorted or not, and then that can be the e-stop. And it could be either a normally open or a normally closed. We could change it in software. The usual way to have e-stops is to have them normally closed, because then if you have a cable failure, like the wire to the emergency stop switch breaks, it's effectively the same as if you've activated the e-stop. So the idea is that it fails in a safe way. It fails in a conservative way that means the machine will stop doing whatever it was doing, and otherwise it can silently fail and you won't know until something goes wrong and you try to hit the e-stop button and nothing happens, because the e-stop is normally open, and then you hit the button and it closes and there's nothing to detect. Anyway, you get the idea. I think that's it, kind of, for the surface mount parts at least. So, what now? What now, indeed? It didn't even look like there were any short circuits on these pins. It looked like these pins all flowed nicely, so I don't need to hit them with the flux and and reflow it or anything with the with the soldering iron. I think that's okay. Now, I kind of hadn't really thought a whole lot about what I was going to do here other than assemble this board. So I could put on the power switch. I could, let's put on the module. See, down here, there is a power supply module, and I was lazy with my decision with this. So this is very much a V1.0 board. I need to find my box with the power regulator modules. And so what I've done is relied on external modules a bit, which is why there is so little on it of the surface mount parts. It's ultimately I could probably just incorporate, here we go, I could probably just incorporate a regulator module, like not a regulator module, I could build a voltage regulator circuit that goes directly onto the PCB. But the lazy way is just to get something like one of these regulator modules that cost like $2 or some crazy small amount and put that in. So got to align the arrows. It's inside positive, negative, out positive, negative. It gives us 5 volts out for a reasonably wide voltage range. So I'm just going to get some headers. What I could do, what I should have done is done a footprint for this that allows this to be surface mounted, so that module could just sit there. You can see it's got the castellated pins on the end. You probably can't see. Let's stick it under the microscope. So it's got the through hole, it's got the through hole holes here, and then what they've done is they've just put pairs of through holes and then just cut the PCB. In fact, look how this has been cut. It's on quite an angle. It's not a milled edge at all. That has been cut with a guillotine or something, or like a rolling blade that cuts through the board. And it's just been mechanically chopped. And so what they've done is they've chopped through the center of these holes, which leaves half a hole exposed with a plated inner. So you can solder into that onto a surface mount pad. But I wasn't clever enough for that. So instead, I'm going to use some header pins. Header pins, what will I use? Just looking for miscellaneous header pins, and then I'll just cut some off into pairs. What do I need? This is way more than I actually need to do the job, but I could just put one pin in each corner. But what I can do is go there and there and there, putting 2 pins in each corner. Before I put it down, make sure that it is correct. 2 pins in each corner just makes it more stable when I'm trying to get the pins in. Come on, wriggle, wriggle, there we go. So the module will now sit, which way is the camera? There we go. So as you can see, the module will now sit above the PCB, which helps with cooling as well. Well, it helps with allowing airflow around the module, but what it does not help with is thermally coupling it to the main board, which can also dissipate heat as well. So, yeah, I don't know which way is better. What do I use to? I've got to find something to sit this on. What I normally use is this little pin header snapping tool. Usually works pretty nicely. Like I can sit a board on that, and it means that the pins on the bottom are not touching the bench, so it's easy to solder onto. And what do I need? I'm going to go for the really big tip on the soldering iron. Oh, hang on, I've got to get this back over there. So yeah, very large tip on the soldering iron there. And I also want to get a bit of fume extraction happening. This is, in order to get this under the camera, I'm soldering somewhere quite different to where I would normally be working. I'd normally work further to the right on the bench. So I've got to bring the little extraction fan thingy over here. And get some soldering happening. Come on. Why can't I get that in? That's it. So what I don't want to do is put on parts that will prevent rework of surface mount parts if that turns out to be necessary. Come on. But the voltage regulator module is kind of important. That's got to go on before any other testing can be done, unless I powered it from a bench supply or something instead. Okay. I'll just solder on one and make sure everything is sitting straight and square. Yeah, looks okay. Seems acceptable. So it's time to solder on some more. There will be thermal conduction through the ground pins. That's actually one of the other reasons that I like putting double pins into these. It helps with the thermal conduction from the ground plane of the module through to the ground plane of the carrier PCB. Helps spread the heat, share it around. And I think I must be almost going for a record for how long I can live stream without looking at the comments. Is there anyone still there? I don't know. Catching all the pins. 0 pins on the floor. Success. Alright. Now, kind of scratching my head a little bit about how to go about testing this. I don't really have test code or anything. I need headers on there. I need standoffs. I think the next thing I should do... no, I'm pausing over this. Okay, what's going through my head right now is... If I find... Where did I put the module? I had it right here. There it is. It is right here. So, this module, this is going to mount on here, which means I need a pin header in there that this plugs into, but I need to set the height, how far this is going to be away from the board. Part of that is in relation to clearing components that are on this touchscreen module with pins that are sticking down through here. So I think I do kind of need to go further. I need to put on anything that might stick down through. What's going to be the worst case? Oh, right here I have the switch. Ooh, let's see if the footprint works. Whew, success, it does. So this is the power switch, and it has pins that come down through. This is probably the thing that's going to protrude about the most, and I think that is going to be reasonably safe. So it doesn't need a stack of clearance above this. So there's a sequence to go through here. The specific sequence when figuring this out for the first time on a new build is to work out the minimum clearance that you need for the second board to go on and put on spacers to suit that clearance. Then put pin headers in place. Mount this on the standoffs without it being soldered in place so that the pin headers are at the perfect height, and then solder them all on. So that helps you set the distance between the boards. Now before I do that, I'm just thinking about what's going to happen here in terms of clearance. Now the pin headers are going to be on the bottom of the PCB, which means they get soldered on the top. The headers for the stepper drivers go on the top, which means they get soldered on the bottom. We're going to have a row of plastic along here, which will make it difficult to get to the other side of these pin headers. So I'm going to do the pin headers before I do the headers for these drivers. Is there anything else I need to take into consideration? I don't think there is. The other thing is that once I put the pin headers on, this board is not going to sit flat anymore. It's going to be sitting up at an angle, so anything I do, it's just going to be a little bit more awkward. But I think that we are at the point now where I need to put the heat set nuts into here, so let's do that. Let's grab out some heat set nuts and solder them. In fact, I'm going to do at least the first one of these, probably all of them, under the microscope, because it's kind of cool, and that way we can see what's going on. Where is that HDMI switch? Okay, so that right there, and let's zoom out a little bit. That right there is where we are going to mount one of these heat set nuts. And I'll take that, drop it in place so that it sits right there. And because these are brass, they solder really easily. And these holes are tinned, so it's just like a hassle finish on the PCB. Now, I've already got the high thermal mass tip on the soldering iron. Like for reference, the soldering that I was just doing, look at the size of the tip on the soldering iron. And I actually use this tip quite a lot. There are two that I commonly use. My favorite general purpose tip is this one, the K tip, the knife tip. And what I've got loaded in the iron right now is this much bigger one, which is really good for connectors because it's got so much thermal mass. Now, let's just introduce the solder to this and see how this goes. So I've got thermal contact onto the base PCB. You can see that it's flowing. Oh, and you can see that I've discolored the brass. But the heat has traveled all the way around quite effectively. And that heatset nut should now be soldered to the board. I'm just giving it a little while. You can see it's taking a while to cool down. It might be too late for you to see it now. But you could actually see the solder solidifying. If I touch this, it's solid now. But because there is so much thermal mass in combination with this brass going into the ground plane, in fact multiple ground planes on this carrier board, you've really got to wait a little while before it has cooled down enough for the solder to be solid. And if I put this on its edge, let's see if we can see this. Yeah, see that? So the heatset nut is soldered to the PCB and it should be pretty solidly attached. So now I've just got to do the same thing 3 more times. So drop in the heatset nut, make sure it's all sitting down flat. Doesn't have to be perfect, but it will kind of tend to self-center. So you can see the heat flow around the around the nut, taking the iron off. You can see it continuing to sort of bubble because there's still a bit of flux and things in there. I'm going to put tweezers on the top and you can see it's still soft, it's still moving. But what I'm going to do is put tweezers on top and reflow it again while I'm pushing down on it, just to make sure that it's sitting flat. And I'm going to leave it still and let the solder cool and harden without it being disturbed while it's cooling, because otherwise it compromises. In fact, you can get little crystalline structures. But you see this here? That finish there is not a good sign for a solder joint. It looks kind of crystalline, like burnished. It should be nice and smooth. But this is, I'm not really that fussed. This is just mechanical mounts. It's not going to be under a huge amount of stress or anything. It's just to, for mounting. There we go. Let that one sit for a minute. And bubble, bubble, toil and trouble. And now you see the little spots appearing on the white plastic down inside the hole because they're as the flux boils out of the solder, if there's moisture and impurities and things, then what happens is you get little explosions coming out of the solder. So you get balls of solder jumping off and balls of flux jumping off as things like moisture boils and expands. Come on. Yeah, you get pressure pockets building up inside the molten solder, which then causes little explosions, which ejects dots of solder and flux and things. And I think that's it. So yeah, so we've now got 4 standoffs soldered on that board. Now 2. Where are we? Yeah, so these pin headers are, I believe, 2mm pitch. They're not 2.54. Oh, creaky, creaky. Oh goody. Yeah, so I've got pin headers here in the standard 0.1 inch pitch, which is 2.54. I've also got 2mm and 1.27mm. But I'm pretty sure these ones are 2mm. Good old metric, as they should be. So I've got a pack of dual row 2mm pin headers here. Seems correct. So let's cut it off at the appropriate spot, which is right about there. Seems to be directly in half. Yeah, that makes sense if it's a 20 pin header. Ooh, I got slightly into that edge. I'm going to put that one aside and use this one so that we've got secure pins, and just clean up the end diffraction. Yeah, didn't really need cleaning. Okay, so I need to look at spacers. So I'm going to need very, very small spacers here. If I push this header in and mount this on top where it's going to go, what I need is spacers to go in here so that an M3 bolt can go through into the threaded insert. And what gap do we need? And because I've been not cleaning up after myself, making a big mess on my bench, my calipers are under things. So what have we got? We've got a space of 3.5, 3.6, 3.8. Yeah, we could use 4mm spacers there comfortably. I don't even know if I have 4mm spacers. Those are I do have 4mm spacers. Fantastic. So I've got little nylon 4mm things, and then I'm going to need what length of nut. So it needs to be 4 plus the thickness of the PCB, rounded up to 2, so that's 6. Plus it's got to go into the threaded insert by a couple of millimeters. So we could use 8 to 10mm bolts. Let's chuck in some 10mm. It shouldn't be too long, but I will check as it goes through the PCB to make sure that it does not over insert. So we don't want it to go through the PCB, through this PCB, and then through this, and then damage whatever is on the other side of here. So what I want is a 4mm insert in the middle there. 4mm seems too much. Let's see, 4? That really seems too much. How did I measure that at 4mm earlier? Or maybe these aren't 4mm. What are they? They're 6. Ah, the label on the thing lied. Unless I just read the wrong thing. Oh, I did. It's they are 4mm internal diameter, not 4mm length. So how am I going to do this? I don't have any that are 4mm long. I think I am going to just use 6s if that pin header can be made to reach. So as an experiment, let's just try it. And I'll probably need longer. Yeah, I'm probably going to need longer. I might need 12mm instead of 10mm bolts. But this is where the standoffs that Austin used would be better, because it's really awkward putting something like a spacer in here and then putting a bolt through without everything falling apart. I'm just going to put a couple on here. I'm going to put them on diagonally opposite corners to see what the spacing is like on that pin header, to see whether it's going to be feasible to use 6mm spacers. And you can see that the pin header in here is not really going, it's not where it's meant to be. It's sitting way higher off the plastic. I probably could solder it on like that, but it's not designed to work like that. Hang on, there is a little bit of flex in this PCB because the corner mounting things are not quite straight. So I'm just going to put in all 4 corners, finger tighten it, and see where the pin headers end up. Alright, so that is approximately how it's meant to be, except for the spacing on the pin headers. Now, I could move the pin headers back a bit this way so that they are not fully seated into the other, like into the socket on the module, the LCD PCB, and then the pins would protrude enough through here that I could solder them. But I'm not sure if that would give me a good electrical connection. What I really need is 4mm spacers. And if you look down, let's see if I can get the angle there. If you look down through the gap between the 2 boards, there is lots and lots of clearance there. There is nothing that's going to cause any interference between those 2 boards. And if I get the power switch and stick that in, you can look down there, you can see there's masses of clearance. So I could very easily go to 4mm spacers and not have any internal clearance problems there. And making things shorter that way, like just not making it any bigger than it needs to be, is always good. And the thing is that we haven't even put connectors on here yet. There are going to be pluggable screw terminals coming off the back here that stick off a long way. So this whole structure, and look at the switch too. So the switch sticks up a fair distance. The whole structure is going to become quite a bit deeper because of the high profile components that I haven't installed yet. And then the modules are going to stick up here. So we're going to, like the stepper driver modules, they're going to be up on headers, and then some types have heat sinks on them. So the modules could stick up like right out here somewhere. A really long way. They could be sticking up 15mm above the PCB. So what am I going to do about 4mm spacers? There are a few options. I can cut them. Cutting them never really works very well. I could 3D print them. What's the time? It is 11:38. We're already getting a fair way through time. If I was not doing a live stream right now, my inclination would be to 3D print them. And they would probably print in about 10 or 15 minutes. So, but I wouldn't have them done by the end of the live stream. Cutting is also not a good solution because I have cut these little spaces many times and they never ever end up accurate. These ones are particularly bad. I wouldn't bother cutting these. So if I was going to cut some to length, in fact, stuff it, I'm going to cut some to length. What I would do is start with much longer ones, not start with a 6mm spacer and then try to cut it to 4mm, because you're cutting off a very small amount. It's much easier to work with when you're just cutting somewhere that's not near the edge of something. So what I'm going to do is start with some of these spacers. Can you see those? Yep. I don't even know what length these are. I just grabbed them because they were longer. 2 reasons. They're longer and they're thinner, 12mm, which means they're going to be easier to cut. So if I take off, I hand tighten this just a little bit too much. If I take this off, so this is the 4mm spacer I've been using, you can see that it's much bigger diameter externally and it's much thicker. So cutting this is going to be a lot harder and less accurate than cutting this. So I'm going to start with this and try to cut it down to 4mm. What did I say there were? 12mm. So I need a third. But yeah, trying to cut across a small plastic cylinder like this and get it to a precise length is really hard unless you've got some kind of a jig set up. So 4mm. Come on, where is it? Right there. And the problem is that I can never get them straight as well, the blade always tends to wander off. If you use cutters, it flattens it, and then you end up with a really nasty shape on the end. If you use a saw, so what I've got here somewhere, I've got a razor saw. So this is a saw with extremely fine teeth. It's like a cross between a tenon saw, which has got the thin blade with the reinforcing on the back, and a hacksaw, but much smaller teeth than a hacksaw. A really fine blade. And if I, what am I going to do this on? Let's do it on here. If I just try to do it like this, I am probably not going to get a straight cut, but I'll try. Oh, and the problem is I need like a tiny little miter box. How about if I grab it through like this, but not through to the point where it's still going to move that way. Let's try with these pliers. And then try cutting it like that. This sort of thing is, if you are doing this one-off for a prototype, this is okay. But this is not something you would ever want to have to do manually if you were making a bunch of these things. Come on. Yeah, so with this one, it's ended up not quite straight, which is exactly what I was thinking would happen. The cut side is not quite parallel, like not perpendicular to the main body of the thing, and not parallel to the factory cut face. So this is the sort of part of a project that can be very fiddly and annoying. It's not as fun as the sticking on the solder paste and putting the pieces in place on the PCB, but it's part of the project that still has to be done. And I don't want to rush ahead and do the other PCB assembly without getting the mechanical aspect of it right. I mean, right now I could solder on the switch and the connectors and the other things, but there's no point if the connection to the carrier PCB is not, is not sorted. Now it's looking like it's shorter than 4mm. Yeah, so the other difficulty with doing this without a jig is getting them consistent. So I find that when I'm trying to make spaces like this, they end up slightly different lengths. Alright, if I just stop talking and get into it, it wouldn't be so bad. I'd probably be done by now. So, dot there. You know what I do need is a drink. And I have one over near my computer. I'll get to it in a second. I'm still going on this record of how long can I ignore the chat. I have not even glanced at it since, what did I say earlier, 10:20 or so, give or take, was last time I looked at the chat. So what I should probably do, before I totally run out of time, what is it, 11:44? Yeah, and I can't really run late today because we're going out for lunch, which is a sentence that would have seemed crazy not very long ago. Seems a little bit crazy now too. Okay, This is the last one. So before I do run out of time, hopefully I will get at least as far as having this mounted and the header on. In fact, once it goes past this point, the final bit of assembly should be very quick. It won't really take very long at all. This is a sadly fiddly part of the process. All right, let's try this again. Try this again with feeling. Okay, so I want that on there, but this time I'm going to use these little cut standoffs. They just fall all the way through. That one fell through as well. 3. Okay, it's because I'm not putting pressure on this. These may actually end up being slightly too short, which would not be good because then it's putting pressure on the PCB, bending it around the header. But I'll be able to judge that. Yeah, it looks like it is slightly. Maybe I need about 5mm standoffs would be ideal. So I am going to... Oh, this is ridiculous. Keeps falling through. All right. Try again. Nope, falls through. Yeah, I am going to design 5mm standoffs. I'm just going to do them in Fusion 360 and print them. It's like the simplest thing ever. 1 sketch, 2 circles, 1 extrude to make a cylinder. And how are we going? Yeah, not too bad. Alright, I'll put on the ones over on the other side away from the connector. Oh, before I can screw that right through, is it going to go too far? No, it's not. I could use an 8mm there instead. In fact, before I screw that in, I'm going to put the... I've managed to lose one of my spacers. It's probably stuck in the middle of the assembly there somewhere. It was. It was right in the middle. So I'm going to put this one on and see how far it protrudes through, because I don't want to do up the other bolt and have it damage anything. So this one I'm going to do up, and what I'm looking for is the head protruding through there. You can see that it's only just coming through the PCB, just a little, not the head, the end of the thing. So this one should be safe. All right, so I'll put that one through. No, I'm going to switch to 8mm. 10mm is just unnecessary. It's coming through the other side of the board when it really doesn't need to. It could be shorter and still go into that threaded insert nicely. Is that it? Yes, 8mm. Yeah, it goes into, it's got plenty of turns on it. So I'm going to change these other ones for 8mm as well. Once I go to 5mm spacers, like once I 3D print some, maybe 10mm would be okay. So you might be wondering why I'm proceeding with this when I'm going to, I've been going on about getting the spacing correct, and I've said that I'm going to do 5mm spacers instead and 3D print them. So why am I bothering to continue with these cut 4mm spacers? Well, that is because I think it's going to work out okay to... yeah, I'll replace this one as well. The positioning on that pin header is still going to be all right. It's going to end up with the pin header soldered in place with the plastic hard up against the PCB, but that's with the 4mm spacer. But with the 5mm spacer, what will probably happen is, so if we're looking at it from this angle, it's a bit hard to tell because of parallax and things on the camera. I'm going to get a straight edge. The PCB is actually slightly bent. If I sit this on here, what's happening is that the spacing here is being held out by this header, and then the ends of the PCB are bending slightly in that direction because the spaces are just ever so slightly too short. So there is a slight gap between the ruler and the PCB here, and a slight gap here. So the shape of this top PCB, I'll exaggerate it, is curved like that because it's being squeezed down on the edges and it's putting pressure on this connector. So by going from 4mm spacers here to 5mm, we'll just relieve that pressure on the PCB, but it will still allow plenty of engagement of that header. So what I'm going to do is just ease those off so that it's no longer bending the PCB down. The PCB will now be sitting flat across that header, and then I'm going to solder the header on. And what is the time? 11:52. That's probably going to be just about the last thing that I can do. Let's go gadget microscope and fix that focus. Now, one thing that I've done is on this header, you can see that there is a border around some of this. Now, these particular pins here have got a solid border around them. And what I've done is put a border around the pins that are used. So these ones you can see, these are ground pins. Those are all used. I'd only need to connect one of them, but still, they're active in the circuit. So all of these pins that have got a border around them, these ones here, are active in the circuit. These two here, these ones here. The ones that don't have the border are not used. Well, not used by me anyway. So what I could do is just solder the ones that I care about, but I'm going to, still got this huge tip on the iron. Let's do a bit of drag soldering down here. Yeah, I'll just solder them all on. I need to clean up this soldering iron tip. Should be a bit better now. Still got a bit of crap on it, but oh well. Now that one was, oh, my stomach is going a bit crazy. It needs something in it. A bit of thermal mass on those ones because there are some ground pins there. Gotta clean the iron again. It's not dragging very well. Okay. Spin the board. Oh, that was a dodgy joint. I probably should be using the, actually I'm going to change tips on the iron. I'm going to switch over to the K tip. And this is one of the things I really like about these style soldering irons is I've just changed the tip on the iron while it was hot with no tools, and I have a different tip on now. And it's up to, like, it's at soldering temperature. Oh, come on. I'm being a real klutz today. Oh, look at that, I needed to clean that tip before I started using it. I'll fix that hole in a moment. Come on. Yeah, I'm not really getting good heat transfer onto the pins. You can see that the solder is globbing up. I should probably, in fact, let's do what I should have done and flux it up. I don't normally bother with this for headers, but it makes stuff better. Flux makes everything better. Get that tip clean again. All right, Now we're going to have a lot of smoke, but hopefully we'll get a bit of better thermal transfer happening. And it smells good too. No kids, you should not breathe flux if you can help it. Do not inhale the flux. Right, that is an embarrassing looking soldering job on this header. I'm going to clean that up a little bit. Spin it around and reflow down here. And you can see the solder distribution on the pins is a bit uneven. There we go. And that should be better. Oh, there's these ground pads here. Got a bit of thermal mass, and you can see that the solder has globbed out towards one side because I was drag soldering in this direction, and the solder has followed the iron. So on those ground pins, I'm just going to reflow it a bit to let it find its happy place. And these ground pins up here are also looking a little bit like potatoes. Okay. Good enough for government work. Oh yeah, and that one I screwed this up. Let's see if that'll flow out. No, it won't. All right, I'm gonna have to go for fixing my mistakes. Fix, come on, fix. How much solder did I get in there? Fix, there, fixed. Very good. Now, what else am I going to do? I'm going to remove, I've got crap collected all over my bench now. I'm going to remove this board from its home and start putting on some of the other through-hole parts. And before I put it back on again, which is going to have to be later, not on this live stream, I'm going to make 5mm spacers so that when it gets stuck back on again, it's going to be at its correct spacing. Come on. There we go. What'll I put on next? Pin headers, I think next to go on will be a couple of pin headers, which means I need my headers local cache again, or cache, depending on whether you're American or not. Let's use some different colors. Instead of black, these are going to be some external connections, so I'm going to use yellow just to make them look different. No real reason. Put that one on there. A little bit of blue tack. Put that one on there. Another little bit of blue tack. Blue tack sucks when you're wearing nitrile gloves because the gloves are kind of stretchy and the blue tack sticks to the gloves. So I'm just going to do one pin on each of these because I haven't actually gone to any trouble to line them up. I just kind of squashed them in and jammed the blue tack in there. So what I want to do first is get a fingernail onto the middle of the plastic and apply pressure, reflow that joint. And this one, fingernail on the plastic, apply pressure, reflow the joint. And then they should sit straight and even-ish. It's even-ish. Even-ish. So then I can do the other pins on those headers. what else am I going to put on? 6-way IDC headers. And because I ended up squirting flux all over that, I now have flux on my gloves, which means the flux is now being transferred to whatever I touch. Oh goody. And that's why I'm wearing gloves. Because now I do not have flux on my hands. And same sort of deal. Hold it in place with the... trying to keep my head out of the camera view here. Looking at it from a distance. So one pin on each of those headers. Take it off. Apply pressure, reflow. Pressure, reflow. And now we should have 2 headers that are sitting nice and flat, so then I can just do the rest of them. Well, I haven't got as far as actually powering it up or doing any testing, and sadly I'm not going to get a chance to on this live stream. But at least it's going to look okay. Don't know if it works, but it's going to look nearly complete. All right, I'm going to put on the... It would probably make sense to put on the stepper headers next, the stepper driver headers. So let's do that. What do I have? How many pins long are they? Looks like they're 8. So I need some 8-pin sockets, and I may only have, oh, what is that? That's an 8? Yes. Oh, and then we need the big capacitors that go in the middle of them. Ah, all right. So what I need is a couple more. I've got some stackable headers here, which I will use if I have to. And then I really am going to have to end this live stream. I really should have ended already. But, okay, what I'm going to do is I am just going to solder on one of these stepper motor driver headers. So I'm going to put that on there, and I'm going to keep it aligned. What will I use? I need a double row pin header. Come on, surely I've got something in my little container of odds and ends. Here we go. Okay, so a double row pin header, because these will be on a 0.1 inch spacing acrossways. Stick it through like that, and that holds everything nicely aligned, so the vertical spacing will be fine. So what I can do then is just sit this down on the bench and do the usual thing of solder one pin on each header. In fact, I'm just going to solder one pin on one header because they're bound together by that cross piece. Apply pressure, reflow, and now it should all be sitting flat. So then I can solder on the other pins, just trusting that it is going to be flat. I think they will. Because where I want to get to with this is at least having one of those big electrolytic capacitors in place, just to see what will fit in between the header for the stepper driver. There is so much more to this. I've done, in the same PCB run, I had some PCBs for 2 different custom stepper driver modules, and yeah, which are for different purposes, not actually for driving steppers. So what I need now is my big box of capacitors, because I have like a whole lot of different electrolytic capacitors here in this big box, all different values and sizes and things. And what I want to do here is just stick in the biggest capacitor I can fit in that space. What have I got here? 100 microfarad, 50 volt. 50 volt seems a bit excessive, but you've got to allow for derating, and we might be running it. In fact, that is pretty much ideal. So I have one that is a bigger value. Oh, 470 microfarad 50 volt. I wonder if these will fit. Oh, just. I think that is what I will go for. I've got to allow for the fact that there's going to be another PCB sitting on top here, and this capacitor slightly protrudes above the header, but the module that goes on top of this is going to have, it's a 2.54 millimeter plastic spacer and then the PCB, so it would clear. It's kind of tight though, so I'm going to see if I can find another one. So that is 470 microfarad 50 volt. I don't really want to go much below 50 volts because you kind of have to halve the voltage rating on electrolytics to derate them. I think those might be the best option I've got at the moment. So, and I can take it out and change it if I have to. Which way around does it go? It is positive down, positive up. Which way? What's that? No, positive up on these capacitors goes that way. So I'll just bend the leads down. Just got to make sure that's correct. V mote plus minus. Yeah, so feed that in through there, and you can see that it protrudes slightly into the space of the next one, but that's okay because the next one is going to be slightly offset that same distance. It's going to be tight on the back of that switch though. Right, so it needs to go about there. Let's solder that one. And cut off the leads. No shooty leads. Okay, so I'll just need to do the same there and there. But I think I really am out of time. I'm actually pretty close on this. There is not a huge amount more assembly to do. It's just about at the point where I could plug it in and start doing some testing. But I really do not... Cable tie says, what, no polarity markings? Yeah, actually there are polarity markings. But they are obscured by... where is it? Yeah, there are polarity markings. Oh, I can't see it now because... hang on, I'm going to switch back to here. So there are polarity markings on the PCB, but they are obscured by other silkscreen from other labels. And yeah, it was easy enough to work it out just by looking at it. Well, I hate how sweaty my hands get when I'm wearing those gloves for a while. Okay, where am I? I'm back here. I have not seen a single thing in the chat for the last hour and a half at least, other than what's right at the end here. And I really do have to go. In fact, I can see my wife coming out to say, we've got to go. So, I've got to wrap it up right now, and I will finish the rest of this board off live stream, and I will talk to you all really soon. But first, I've got to unlock my laptop so that I can switch to this, and I can end this live stream. So, thanks for coming along. Hopefully this was a distraction from the doom scrolling and a little bit, I don't know, a little bit of therapy. It was therapy for me, even if it wasn't for you. So, thank you very much, and I will see you all really, really soon. Bye.